We're recording. Excellent. So, hello everyone, and welcome to the final video in this little series of stable isotope data analysis videos. And in this video, we're going to have a quick look at how to run the OR package Trophic position that was developed by Claudio Quezada and Chris Harland, Andrew Jackson, and a few others a couple of years ago. That's kind of applying it does sort of apply a Bayesian framework to the calculation of trophic position that we discussed right at the beginning of these videos. Sort of when we start either with a one source or a two source mixing model, estimating the isotope ratios or knowing the isotope ratios of the putative prey source, knowing the isotope ratios of the consumer, and calculating trophic position based on those. One of the issues with the previous approach is, same as the issues of the mixing models, that we don't have any way of incorporating estimated variance in the prey values, or we don't have any way of incorporating variance in the trophic enrichment factors. So as we saw with Simmer and Mixar and so on, a Bayesian approach allows us to bring in variance in those different factors. Also, I'm going to pretty much follow the same format we did before. I'm going to show you some of the files here, and then we're going to run through a worked example. So the first thing I want to say is similar to what we had previously. I'm just going to share my screen. Yes, this one. Excellent. Similar to what we had in the previous videos, that because we're dealing with an OR package, we have to have data going in a specific type of format. Yeah, and I've provided some just called TP here. We'll have a look at that in a moment. That's data is kind of formatted the way we need it to be. So what we want to do is, as we've done previously, is open up OR Studio, create an OR Studio project in the folder that file is in. And then we can start, let's see, we're going to tidy this up a little bit. Get rid of that down there. Okay, and then we can start running the actual analysis. So as before, we've got some notes and things like that in here. And you can sort of follow through, and you have all of these files, and you can run this, and hopefully everything should work. One thing to note with this, you can use the typical install packages to install trophic position, or you may want to go, no wonder it's not work, and install the packages directly through OR Studio. One thing we've had some issues with in the past is a conflict between different versions of particularly trophic position and CRAN, where we get our OR packages. So if you run into some issues with that, you can just install a package directly from Claudio's GitHub page, and the script is in there to show you how to do that. But I've put the little hash mark or pound sign, depending where in the part of the world you live, in the head of that, just to stop those scripts running if we click it. But if you click run here, it won't run any of that. We'll run this. We've loaded up the packages. So the data set we're going to work with here is a little bit different. It's not the rivers. It's not the it's not the Finnish lakes, the Scandinavian lakes, or Nordic lakes, I should say. Rather, we're dealing with data from a paper I published with a couple of colleagues here in Canada a few years ago, where we're looking at larval sea lamprey, which live in the rivers around here. And they're a very, very cool type of fish. And as their larval stage, they live for a number of years, typically buried in river sediment, and they will pop up and feed on detritus and debris flowing through in the water column. And we were sort of using a multiple isotope approach to try and get a better handle on what type of resources were fueling these lamprey. And there's a link to the paper here. But for now, the key point is that we've got some of the data from that paper is being, we're going to use this here, and we're going to call it, let's get rid of these quickly, and lamp.tp.data. So we've got river, we've got a number of different rivers, the Nashwaak, the St. John, the Catamaran Brook. We've got a couple of different species, 3-spine sticklebacks, some invertebrates. We've got biofilm samples. We've got some fish. These BNDs, black-nosed dace rather, brook trout, chronoids, and in here somewhere we should have, here we go, here's our Aniseed lamprey. And we have carbon and we have nitrogen isotope ratios for those. And you will notice that I've broken one of my prime rules here, and I've got my isotope ratios in here with 2 decimal places. So that's a slap on the wrist for me. And yeah, do as I say, not as I do. Eh? So maybe we want to generate some summary stats and plot these out for exactly as we've done before. New data set. Let's have a look, make some plots, get a handle on it before we start doing anything too intricate or too complicated. So I'm not going to go through this in much detail, at least the mechanisms of this. We've done that in earlier lectures or videos. But we want to plug all the data in and create a summary biplot. And I'm going to blow this up, make it a bit bigger so it's a bit easier for you all to see. Okay. So what we have here, we've got our data separated into these 3 rivers, Catamaran Brook, Nashwauk River, and the St. John River. And then we've sort of summarized various different sources and consumer groups that we're interested in. And we've got our pooled fish species here. We've got our pooled BMI, so benthic macroinvertebrates here. We've got our biofilm values there, leaf litter values down there. Now that's typically the 2 sources we think are probably going to be fueling these extreme food webs. And then in these blue crosses are the Aniseed lamprey. So straight away we can see something very clear. We can see that the Aniseed lamprey are feeding very differently to the majority of other fish species in the system. There's nothing else like that. And facultatively, they're probably feeding more similar to an invertebrate than anything else. But even still, they have a completely distinct isotopic niche within this community. So I think these are a really cool species of fish, and this is one of the reasons I think why. So one thing we might want to do, or one thing we're going to do, is try and estimate the trophic position of lamprey in these 3 rivers. We can see that they've got very different nitrogen values, but right across the system in these 3 rivers, we've got very different nitrogen values, even from the leaf litter in the systems. We've got nitrogen values differing by 3-4 per mil between the systems. We've got some differences in biofilm, and in some cases we've got big differences in the invertebrates, but not always, not necessarily between Catamaran Brook and the Nashwauk. St. John River is a much bigger river than either of those, so everything's a little bit elevated in nitrogen, a bit more productive. Not that surprising. Okay, so we've plotted the data. Looks good, looks interesting, pretty much doing what we expected it to do. So we want to go in and calculate some estimates of trophic position. We could do this using the methods we talked about earlier in the class or in the course, where we just take the mean value for leaf litter and the mean value for biofilm, nitrogen values, and estimate trophic position from those. But here we've got multiple samples for each. We can see there's a reasonable bit of variation, certainly in nitrogen or in carbon in some of these samples. So that's something we want to be able to quantify and incorporate into our mixing model, and then ultimately calculating trophic position. So how do we do it? Well, the first thing we need to do is to define various characteristics of the model, similar to what we did with the simmer and mixer. All the hardcore mathematics goes on under the hood, but we have to tell it what the different values are. And the first thing we need to do is assign our trophic discrimination factors, so our TDF values. There's a couple of these that are built in as not as default data sets, let's say, in the trophic position package. But you can also define your own. And again, there's a lot of information on Claudio's GitHub page that goes into a lot more detail about how to do the various different steps in this. I'm going to work through sort of one example. If you're going to use this package, I suggest you also go in and read up a little bit and work on from there. Fix the typos as we go. Okay, so we run that. In this case, what we've done, we've just taken default values, and these are from that very famous post paper we talked about. 15N values 3.4 plus or minus 1, and 13C values 4 plus or minus 1.3. So again, key point here is that we're able to incorporate this variability into the data set. So we've set that, we've included it. We can run this and have a sort of another way of sort of plotting the data and having a quick look at the data. And this is a setup that Claudio put together. And it's pretty neat that we can generate for each lake. We can get some of the standardized data. And it's going to take a little while to run through all of this. So it's basically outputting summary data for each, I said lake, I should have said river system. So for each river system, each mixture essentially. So we've got set consumers. In this case, we've got fish, benthic macroinvertebrates, and lamprey are our 3 consumer groups in each lake or in each river. And we've got 2 sources, leaf litter and biofilm. So if we want to take a quick look at one of these, I'll try and pick a good one. Push a button and hope for the best. Okay, so what we get down here, we can look at it down here. So we've got for one object for group catamaran. So this is the river catamaran, consumer is the lamprey, baseline 1 biofilm, baseline 2 leaf litter. And then we've got the number of samples for carbon. And I think these are our baselines. Yeah, these are our baselines. We've got 15 replicate samples that make up baseline 1 for carbon. D13C, 15 samples to make up our carbon baseline. The same thing for nitrogen. We've got delta N and delta C, and then we've got the same thing for our consumers. So all of this, we can sort of see that it's giving us a summary back of the data that we're putting into the model. We can also look at these are quite nice density plots that Claudio produced for this package. Can I blow that up? I cannot. I'll bring this down to be able to see. So this is Catamaran Brook, and here we've got equivalent to a biplot, but here we're just showing each source or each piece of data that's going into each model. Yeah. So here we've got the values for our leaf litter in red, and you can also see the density distribution for those. And it's reasonably spread out, but it's almost normal. We've got our biofilm, very large range of biofilm values in carbon. Pretty tight range in nitrogen. Again, for a lamprey, big range of values in carbon, but pretty tight range in nitrogen. A nice way, again, of just visualizing your data. And if you get any spurious results or things like that at the end, you can always go back to this and try and understand what's going on in the model. Because again, remember, we're running a mixing model in this, and we need to be able to account for variance and error and things like that that will come in associated with that. But for the most part now, everything looks pretty much okay. So we're ready to click go and run the model. One thing worth noting on this is we mentioned a bit about this, about the length of time it can take to run these models, particularly with things like Mixire. Claudio developed a really neat step in the Trophic position package, where essentially here you can, through computer wizardry that's far beyond me, can go in and identify how many different processing cores there are in your computer. And then when it's running the analysis, it will pass that to each core to get all of the cores working to maximize the effort by the computer and reduce the amount of time it's taking. So that's sort of that step there. Another note, I tried to do this earlier today and got an error message because there was a change during an update to RStudio. So if this isn't working, you probably need to update RStudio to the most recent version. Then we need to go in, and this is essentially giving the characteristics of our model. Models, we're using this parallel clusters. We've got lamp list, that's the data that we've put in. Multi-model TP, that's the model structure, say. We can talk a bit about that in class. Lambda is the baseline of the trophic position of the sources. number of iterations, burn-in time, number of chains, different sort of model characteristics. We'll see a thing later on where we don't think this model is quite converged, and you might want to extend the runtime. You can do that by increasing the number of iterations. But remember, when you do that, that's also going to increase the length of time it takes the model to run. So right now, I'm just going to do a short version, so it's easy to run through, and you're not going to press go and have to wait for 5 or 6 hours. This will never take 5 or 6 hours, but even if it takes 15 minutes, it's longer than we want it to take right now. Okay, so you can click all that and it'll run, or you're setting the model up. And once it's gone through, you want to remember to run this little line here just to take out that clustering step from that, so that you're not passing everything to the different clusters within your computer parallel. So that's going to take a little bit of time to run. I probably didn't need to click it, but there we go. And once that's run, essentially the output of that script will be a very large OR object that contains all the results for all the posterior distributions and so on and so forth. And as we sort of discussed in the past, that's not always the most user-friendly type of way of having data. And there's a couple of different things. Claudio has some ways that are already coded into the Trophic position package that allows you to go in and interact with that data and get that data and pull it out. Or we've got some worked examples in here, which will sort of show you how to get some of the summary data that you might want out of these. And this is still churning away here, so I'm just going to scroll down and show you some of these we made earlier. And the first thing we might want to do here is to just get some of the summary data. And here we're not actually getting ourselves at any of the posterior distributions of things. We're just pulling out summary data from the model. So here, what we're seeing here is group, so Nashwauk, and then St. John. We can sort of scroll on down and we will hit the Catamaran Brook. We've got fish, BMI, Lamprey, lower and upper credibility intervals, median or confidence intervals rather, median and mode values. And I think if we scroll across here, we'll get some further values that we might want. We also calculate the alpha value and a range on the alpha values. Yeah. So again, alpha being the contribution of source 1 to the diet. Here, because we're doing a 2-source mixing model. We talked about that earlier in the class. I'm starting to regret pressing go on that, but hopefully it'll just keep churning away there and we can keep talking. So the other thing we might want to do is to actually pull out some of our own summary data. And we can do this by, I'm not going to give you the details of how you do it, but there's a bit of code in here basically that allows you to dive into the posterior distributions and extract them and then make some tables and things like that. So here, essentially what I've done is created a table called TP sum, trophic position sum, which gives us river and class. So river being the system, class being the species, the mean and standard deviation rounded to 1 decimal place. The next thing we might want to do is to generate some plots and generate some figures from this. So again, we've got some script in here that is going to run our model on what we've called here our out test, which is a data frame that we've created by extracting posterior distributions. And this is a piece of script here that's going to give us a box plot for the estimates of trophic position in each system. And because this is still churning away here in the background, what I'm going to do is I'm just going to show you one we made earlier. Okay. And bear with me for one moment. So here, I promise you I can see it and you will see it soon too. Okay, here is that TP plot. Just give it a moment here just to scale it and make sure it looks neat and tidy. And what we're looking at now is estimated trophic position. And this, so here we've got a box plot, and this is a box plot of the entire posterior distribution. And we've got lamprey, BMI, benthic macroinvertebrates, and fish across our three rivers. And we can see things kind of look as we might expect them to do. Lamprey have a trophic position equivalent or certainly closer to benthic macroinvertebrates than they do to fish. Exactly as we sort of guessed by looking at the data. Nashwauk, St. John, everything looks pretty clear. Catamaran Brook, the lamprey particularly are a bit of a mess. The mode values right in the center get. Where does it think I want to have that? Stick. Oh, I can't. Perfect. Let's hope it'll disappear in a moment. Anyway, however, there's a massive tail here. We've got estimates of trophic position of some of these lamprey up to beyond 7.5, up towards 8, which basically means that they're probably eating Tyrannosaurus rexes, which is pretty unlikely, let's be honest. So there's something hasn't quite worked here. And if you remember, if we look back, nope, finished, great. If we look back to here, the actual biplot, and we've got this huge big range of carbon values in the lamprey, and we've got a big range, a big difference in nitrogen values between our two sources, but also in our carbon values between our two sources. So because we're looking at this at as a population level, it's saying there's a huge big variance in lamprey, and that means it's very difficult with the model as we ran it to give a very good estimate of resource use because there's so many different possibilities that it could be. So one way of getting around this is just simply to run the model for a bit longer. And we can do that if we go down here to increase the number of iterations. Excuse me. That will give us a longer model or a longer run on the model. Model's more likely to converge, and we start getting a more realistic estimate of the likely trophic position. And again, we can save that using our ggplot stuff. Right, I do believe that's it. So what I want to do, I'll bring this here back up for a sec. I want to stop sharing so you can see me. The eagle-eyed among you will know that it is now 7 minutes to 5 on a Friday evening. So I'm going to say goodbye. I'm going to go and open a bottle of beer and enjoy my Friday evening. And I'll see you all next week, I guess. All right. I hope you enjoyed this. Bye-bye.